Now for section 6.6, we're going to be talking about the law of cosines. And so together, these two, we had the law of sines from the last section and the law of cosines from this section, will allow us to solve for the different kinds of oblique triangles. And so specifically here, law of cosines are going to take on the two cases that the law of sines could not solve for, the side angle side and the side cases. And so I have here laid out the law of cosines. There are basically two versions of it. This version over here that says something like up at the start, a squared equals b squared plus c squared minus 2bc cosine a. This is going to be used to solve for sides. So side A, side B, or side C. These others here, like a cosine A, cosine B, and cosine C, are going to be used to solve for one of the angles in a triangle. And so depending on what we're trying to do, we can choose any one of these to solve for an angle A, B, or C, or a side A, B, or C. So here's one situation where we can set it up and solve via the law of cosines. It says a tunnel is to be built through a mountain. To estimate the length of the tunnel, a surveyor makes the measurements shown in this picture. Using the surveyor's data, we're going to approximate the length of the tunnel. So what they've done here is they've taken a measurement from one end of the tunnel and a measurement from the other end of the tunnel for distance, and then they figured out the angle between those two. So we have one side, another side, and we have the angle between the two sides. So we call this a side angle side situation, knowing this information. And so what I'm going to do here is we got our triangle laid out with the letters A, B, and C. So we want to know the distance between A and B basically on either end of the tunnel. That would be side C across there. And so what we want to do is solve for what we're going to call side C using the law of cosines. Now to solve for the law for C with the law of cosines. Now to solve for side C with the law of cosines, I'm going to use this one formula that starts out with c squared equals a squared plus b squared minus 2ab cosine C. So here we can call the A is the 212 and the B is the 388. So it would go 212 squared plus 388 squared minus 2 times 212 times 388 cosine of 82.4 degrees. Okay. And so there's a lot of numbers here, but we're basically just going to let the calculator handle the majority of the work for us. So I'm going to show how this goes inside the calculator here. Okay, so we'll just plug it in exactly as it shows it here. Now it's important to make sure we're in degree mode. And when we hit enter here, it'll give us a fairly large number. But thankfully it does terminate. We don't have to round this one off necessarily. So I'll switch back over here and write that number down. For c squared, that's going to be equal to 171,730.2367. But that's c squared, so we're going to take the square root of it. We're only looking for positive solution here, so just regular positive square root of that number. So we can go back over here, take the square root, like so, and that's going to be approximately how much c is going to be. So we'll round that to the nearest tenth. C is going to be approximately 416.8. That measuring the distance here in feet from one end of the mountain to the other end. And so basically the length of the tunnel would be this long. Now for example 2, it says the sides of the triangle are 5, 8, and 12, A, B, and C. Find the angles in the triangle. Okay, so let's lay out what we have here. We have angle A, B, and C unknown, but we know side A is equal to 5, side B is equal to 8, and side C is equal to 12. Now looking at the law of cosines again, the formulas we're going to use to solve for angle A, B, and C are these here on the right. So if we want to solve for A, what we're going to do is use the formula that goes cosine of A is equal to B squared plus C squared minus A squared over 2BC. So we'll just plug the numbers in here and we'll get cosine of A is equal to 8 squared plus 12 squared minus 5 squared all over 2 times 8 times 12. Now we're going to need to approximate this with the calculator again. So let's plug it in exactly as I have it here. Of course, feel free to simplify this as much as you'd like to as we go along before plugging it in. But if we just plug it in straight like it is here, this is what it should look like. Okay, I'll hit enter and it comes out to be this much. And we don't even have to round it. We can just use the whole number at this point. So what we're going to have here is cosine of A is equal to 0.95312.5. And the trick again we're going to use as we've been doing so far is take the inverse, since we're trying to solve for angle A here, cosine inverse of both sides. So we're going to have A is equal to cosine inverse of that number. Now when I took the calculator and I ran the inverse cosine of that and rounded it off, I came out approximately with 17.6 degrees. Now for angle B, we're going to use the formula cosine B is equal to A squared plus C squared minus B squared all over 2AC. So in this case, that would look like 5 squared plus 12 squared minus 8 squared all over 2 times 5 times 12. Similar to before, we'll run through the calculator here. This one I came out with 0.875. So what I'll do is I'll take cosine inverse of both sides here. Okay, and that's going to bring it down to B is equal to cosine inverse 0.875. And running the calculator with that, we come out with approximately 29.0 when rounded to the nearest tenth. All right, so now we've solved for angle A, we've solved for angle B, and we're pretty much done with the law of cosines, because for the last angle, I can take the ones that I've solved for, subtract those from 180 degrees, and angle C is going to come out to be 133.4 degrees. Now for this one example here, we got angle A, side B, and side C. So let's set out here what we're dealing with. Triangle ABC, angle A 46.5 degrees, B is 10.5, C is equal 18.0. And so we don't know side A. So what we got here is a side, angle, side triangle yet again. And so what we can do is use law of cosines. Okay, and we'll need to solve for an angle, and it looks like we need to also solve for one of the sides as well. So to solve for A, let's use the formula that starts with A squared here. So to find side A, we'll plug into that. We'll go a squared is equal to 10.5 squared plus 18 squared minus 2 times 10.5 times 18, and then the cosine of A, which is 46.5 degrees. A lot of stuff there to calculate, but again, I'm just going to let the calculator take care of all this stuff here. So you can just plug it in as it is, let it do the number crunching, and it round it off, and it keeps several decimal places if you need to round off. So I rounded it to 174.05197. But with that, I have to take the square root to solve for A. And when that's done, I got approximately 13.2 for A. Okie doke. So that's going to be what we have as a result of solving for A. Now let's look at one of the angles we have here. Let's look at angle B. So to solve for angle B, let's use this one over here that goes cosine B. Okay, so we're going to use that formula. And if you'd like to practice what we're doing so far, you may want to pause the video and see if you could calculate the value for angle B. When I set up the formula here, cosine B is going to be equal to 13.2 squared, as we've solved for A, plus 18 squared minus 10.5 squared, all over 2 times 13.2 times 18. Okay, another thing where we'll need to let the calculator take care of some different number crunching duties here. All that together is going to approximately be 0.81677. But we're solving again for B, so I need to take cosine inverse, okay, of both sides, so that I can cross that out. And when I do the calculation for B here, the cosine inverse turns out to be 35.3 degrees. And so now there's only one item remaining, and that's the remaining angle C. Easy enough to determine if we just take 180 degrees minus 46.5 degrees minus 35.3 degrees. Comes out to be 98.2 degrees. All right, now on this thing here it says heading and bearing. And we can use some of our law of cosines and also law of sines in some cases when dealing with distances and their heading and bearing measurements. And so here's some illustrations of what we mean. For instance, north 30 degrees east means the heading is north, but it's angled toward the east by 30 degrees. Same kind of idea with north 60 degrees west. It's heading in the north direction, but it's angled over by 60 degrees toward the west. And then south 70 degrees west means it's heading in the south direction, but it's angling over from dead due south by 70 degrees over toward the west. South 50 degrees east would mean it's heading toward the south, but it's angling over toward the east by 50 degrees from straight due south. Okay, so let's look at this one problem here. It says two airplanes leave at the same time. One is traveling at 120 miles per hour in the direction of north, 32 degrees west at a speed, and another is traveling at the speed of 150 miles an hour in the direction of south, 65 degrees west. And so we want to know how far apart are they after 2 hours. Okay, so let's set up our illustration of their direction. North, south, east, west. Okay, the first one is heading north, 32 degrees west. So it's heading toward the north, but we're angling over toward the west by 32 degrees. So that's what that would look like here. Okay, the other one is heading south, but it's angling over toward the west by 65 degrees. Okay, so that's where the angles will go, either angling from straight north or from straight down south. Okay, and so we want to know how far apart are they after 2 hours. So let's calculate how far they've traveled so far. Airplane 1 will have traveled 120 times 2 after 2 hours, or 240 miles. The other one was traveling at a different speed, and so after 2 hours, it will have traveled 150 times 2, or 300 miles. Okay, so let's write that on the picture here to illustrate how far they've traveled. Okie doke. And so what I want to do is construct the triangle so I can solve it. We can do that because what I'm going to do is find the angle between these two sides. So that angle, we can figure that out by taking 180 degrees minus 32 degrees minus 65 degrees. And what we'll get is 83 degrees. So here in the middle, between the two sides, is 83 degrees. Okay, and so what we're going to have here is a side angle side triangle that we can solve. So we're going to use the law of cosines. We could call our triangle here triangle A, B, C. What I'll be trying to solve for is side A. That is the side of the distance between the two airplanes after 2 hours. Okay, so we're going to solve for side A, and by the law of cosines, that'll go a squared is equal to b squared plus c squared minus 2bc cosine of A. Okay, and so we'll get here a squared is equal to 240 squared plus 300 squared minus 2 times 240 times 300 cosine of 83 degrees. Okay, and I went ahead and ran the numbers again on all the stuff here, calculated that out, and I got approximately 130,050.8145. But to that number, we'll have to do the square root because of a squared. And so when we're done with that, we'll have A is approximately 360.6. So 360.6 is the number of miles between the two locations, the two airplanes, after 2 hours. Okay, now in this next example, it's going to be a little bit different, but it's dealing with the heading and bearing. It says a pilot sets out from an airport and heads in the direction of north 20 degrees east, flying at 200 miles an hour. After 1 hour, he makes a course correction and heads in the direction of north 40 degrees east. Half an hour after that, engine troubles force him to make an emergency landing. We want to find the distance between the airport and his final landing point and find the bearing from the airport to his final landing point. Okay, so let's draw out the picture of what's going on here. So this is going to be where we start from. Okay, so this is going to be the airport. that it takes off from. And it says it's heading in the direction of north, 20 degrees east. So it's going to look something like this, let's say. Heading north, but angled over to the east by 20 degrees. Okay, and then after some time, about out here, let's say, makes a course correction and starts traveling north 40 degrees east. So he's traveling at a slightly different angle from north than he was before. Okay, so now the angle over from north is at 40 degrees. Okay, and then it has to land at a location out here after engine trouble. So somewhere out there where it has another landing location. Okay, so we want to figure out, first off, how far is it from where it started to where it landed there? And then we also want to determine what is the bearing from the original starting airport to where it landed, because now the angle is slightly different from its original location. Okay, so let me show you how we can do this. Let's make this triangle look like A, B, C. Now the angles in this triangle that we're looking at here. Okay, I like to figure out, first off, how far it's traveled. After the first hour, it will have traveled 200 miles. And then after half an hour, it will have traveled another 100 miles. So the first leg of the journey was 200, since it traveled for an hour at 200 miles per hour. And then the last half of the journey before it landed was only a half an hour, so it only got to 100 miles before it had to land. Okay, and so we know two sides of the triangle. What I'm going to do is figure out the angle between these two sides. So that'll be represented by angle A. So to find angle A, what we can do is basically we're going to have a 20-degree angle in here, a 90-degree angle, and a 50-degree angle. And so what we're going to have for A is going to equal to 20 degrees plus 90 degrees plus 50 degrees. And so A is going to be equal to 160 degrees. How I'm getting this information is the 20 degrees matches up with the 20 degrees where we started. There's 90 degrees in the middle from the right angle. And then there's 50 degrees here on the lower side next to the horizontal line, because we already have 40, and the 50 is how we get to another 90-degree angle in that corner. Okay, so what we're going to be trying to find is what I like to find is side A over here. That's the distance between the airport and where it lands. So in order to find A, we're going to use the law of cosines. So A squared is equal to 200 squared plus 100 squared minus 2 times 200 times 100 cosine of 160 degrees. So what I got out here was A squared is approximately 87,587.7048. But we take the square root of all that stuff there, and we get that A is approximately 295.95 miles. Okay, so from where it started to where it landed, that's approximately that much distance there. Okay, now that was part A here. Part B is we want to figure out what's the final bearing from the airport to where it landed. So what we want to do is find this angle between north and to the final line direction over to where it landed. So how do we figure that angle out here? Well, what I'll do is I'll figure out the angle inside the triangle. So what we're going to do is find angle C, and then we're going to add to the 20 degrees that we already have there. Okay, and so to find angle C, we can do a lot of different situations here. I'm actually going to use the law of sines in order to find C. We can do that by sine C over 100 equals sine 160 degrees over 295.95 for A. So we'll cross multiply here, do the solution for sine C. Sine C is going to be equal to 100 sine 160 degrees all over 295.95. So what we're going to get here for sine C is approximately 0.115567, to which we're going to apply the sine inverse to both sides so we can solve for C. And what we're going to get for C is approximately 6.64 degrees. Okie doke. So what that's telling us here, that angle, is that the angle between where its original bearing to where it's finally landed, we're going to take 20 degrees plus 6.64. So we get 26.64 degrees. And so the final bearing will be north, 26.64 degrees east. Last formula is to look at something called Heron's formula. And Heron's formula is a fairly old formula equation for figuring out the area of a triangle if we know the three sides of the triangle. And so Heron's formula goes A equals the square root of S times S minus A times S minus B times S minus C, where S is equal to the sum of the three sides and then divide that by 2, or take 1/2. Basically 1/2 of the perimeter. So they call it here the semi-perimeter. We know the lengths of the three sides here. So we can use Heron's formula to determine that square footage, in this case, within that triangular lot. And so for Heron's formula, we'll take S is equal to 315 plus 280 plus 125, all divided by 2. That's equal to 360. So when we use the formula here, A is equal to square root of 360 times 360 minus 315 times 360 minus 250 times 360 minus 125. And basically that's what Heron's formula would look like with these values plugged in. And so it's just a matter of running the numbers to get a value for this. What I got was 17,451.6. That's the area of the triangle, in this case in square feet.